Hello everyone, welcome to our quiz review. We've got a quiz tomorrow, so I just want to run through a few topics that we've covered this week and a couple from last week as well that might pop up on the quiz, and give you one last shot to see some examples with those types of problems and do some practice problems to get you ready. All right, so let's kind of get started here. This very first question, very simple, just asks, is the graph connected? And the way that you can tell if a graph is connected is you should be able to pick any vertex on the graph, and from that vertex, you should be able to travel to every other vertex. In other words, there should be a path that takes you to every other vertex that is on the graph. And as it turns out, I'm looking at this one and I am able to visit every single circuit, or I'm sorry, every single vertex from any other vertex. So I could start here and I could get to every other vertex, or I could start here and I could find a way to get to every other vertex. So this graph is connected. All right, so we would just simply say, yes, it is connected. All right. If I wanted to disconnect it, let me show you a quick example of something that is disconnected here so you can see the difference. Let's say I deleted this edge right here. That would disconnect the graph. And the reason being is because if I went back to that vertex that I started at, and let's say I wanted to travel to this vertex over here, I could go down, I could go left, down, right, and then I could go down. I go over here, but there's no way for me to make the jump from this part of the graph over to this part of the graph where the vertex is located that I want to go to. All right, so this would be disconnected while this would be connected. All right, so that is the difference there. Okay. Let me switch back here. All right, so this next one is just another simple one. What is the degree of each vertex? Remember, the degree of a vertex is determined by the number of edges that touch that vertex, okay? So for instance, if we were looking at vertex A, there's only one edge that comes into that vertex, so A would have a degree of 1. All right, then we just go through systematically and look at each vertex. So B has 2 edges here that come into it, so B has a degree of 2. Then with C, again, I count 2 edges coming in, so it would also have a degree of 2. D has 2 edges, so it has a degree of 2. E has 2 edges, so it's going to have a degree of 2. F is the same way. G has 1, 2, 3, 4 edges coming into G, so it's going to have a degree of 4. And H has 1, 2, 3 edges, so its degree is 3. Okay. Now, determining the degree of the vertices inside of your graph is important because it tells us whether or not we have an Euler path or an Euler circuit, which is the next thing that we want to be able to find. So in this graph, just notice it just says determine whether or not the graph contains an Euler path or an Euler circuit. For this problem, we don't need to actually find the path or circuit. We just want to know if one exists. Okay, so we're going to go through just like we did in the previous problem, find the degrees, and then use Euler's theorem to help us out here. So I'm going to start with A. A's got a degree of 1. Let me switch colors. This is the same letter as the same color as the letters there. So I'm going to switch over here. All right, so A's got a degree of 1. Let's go to B. So we got 1, 2, 3, 4. And just that 1 popping up there tells me that there's no circuit in this graph already, right? Because remember, for an Euler circuit to exist, they all have to be even. So 1, 2, 3, okay. So now we've got some warning lights going off here because we already have 2 odds, and if a path is going to exist, we can't have any more than 2 odds. So we got 1, 2, 3. So this one's got a degree of 3, so that tells me right there there are no Euler paths or circuits in this graph. And it doesn't really matter what happens with E and F there because once we see 3 odds, we know neither exists. Okay, so we would say no Euler path or circuit. And the reason is too many odd vertices. Okay. All right. So let's go to the next one here. So this is an application here where we have some bridges and land masses. We talked about a problem like this way back on the very first lesson of this unit. And this is typical of the type of problem that Euler used to actually invent graph theory. So he was looking at a bridges and land masses type problem. And what he did was he took each of the land masses that were present in the map that he was given and he reduced them down to a single point. So you'll notice that it says draw a graph that models the connecting relationship in the map below. They want the vertices to represent the land masses and they want the edges to represent the bridges. Okay, so for instance, this landmass way up here, all of A is going to shrink down to one single point. So this point represents this entire piece of land over here. All right, and we're going to do the same thing for each of the other land masses. So we have C, D, E, and B. So I'm going to come over here. C's over on the left-hand side. D's here in the middle, E's over here on the right, and then B is down here. Okay, and then it says the edges represent the bridges connecting them. So for instance, I see a bridge that connects A and C. So I'm going to draw an edge from C to A. I see two bridges that go from A to D. So I'm going to draw an edge from A to D, and then I'm going to draw another edge from A to D, and I'll curve it. Okay, and then over here we've got a bridge that connects A to E. So I'm going to draw an edge going from A to E. All right, and your graph that you draw when you draw this thing out does not have to be pretty. You can already see mine. Mine is not pretty. All you need is the functionality. You just need the vertices and the edges to be correct. Okay, so let's go down here. Let's look at B. B connects to C twice. So let me draw an edge going from B to C, and then I'm going to draw another edge going from B to C. B connects to D, so I need an edge going from B to D. And then B also connects to E over here, so there we go. All right, let's see. So if I go back to C, I notice C's got four bridges. I've got 1, 2, 3. So the one I'm missing is from C to D, so I'm going to draw an edge going from C to D. And let's see, E's got one, so we got two bridges connected to E. I've got 1, 2, so we're good there. B's got 1, 2, 3, 4, so we're good there. C's got its 4. 1, 2, 3, 4 for A. 1, 2, 3, 4 for D. I think we've got them all. All right. So this went through, I compared the degrees from the map over here to the degrees over here. One thing you should notice before we start trying to find this next piece are the degrees of each of the vertices. All right, and I'll mark these in blue for you. So this one has 1, 2, 3, 4 edges. So this has a degree of 4. D has 1, 2, 3, 4. So this also has a degree of 4. 1, 2. This one has a degree of 2. 1, 2, 3, 4. And then up here at A, we got 1, 2, 3, 4. And you'll notice that all of the degrees have all of the vertices have an even degree. So there is an Euler circuit that exists in this. And that's exactly what they're going to ask for next. It says determine a circuit that uses each bridge exactly once. Now in the instructions, they don't always explicitly say Euler circuit, but that is the definition of an Euler circuit. A circuit that uses every connecting edge exactly once. That's what an Euler circuit is. So they're really asking you for an Euler circuit from the graph that you just created. And I would recommend using Fleury's algorithm. Right? This is the method that I taught you to use to find an Euler circuit. It guarantees that you will find one. All right, so that's what I'm going to demonstrate here to find our Euler circuit. All right, and I'm going to start at vertex A. And it really doesn't matter where you start. You can start at any vertex if it's a circuit that you're finding. All right, if it's a path, you got to start at one of the odd vertices. All right, so here I go. So remember, the way that we do this is we delete an edge, and we can delete that edge as long as it doesn't create a disconnected graph. Now, before I use the white pen, today what I'm going to do to represent a deleted edge is I'm just going to do this, because I know you guys are doing this on your paper, and it's a pain in the butt to get the eraser out and delete that. So I'll put these little dash marks through the line, and that'll represent that edge has been deleted. And you can use that method on your paper too. I think it might be a little bit easier. All right, so I'm going to go from A to E, and I'll add E to my circuit. All right, and then I'm going to do the same thing. Here I have only one edge that I can take out of E, so we've got to go to B. So we'll delete this edge from E to B, and add B to our circuit. And let's say we go to C, and you'll notice that as I'm doing this algorithm, it's really just a lot of guessing and just kind of checking. You make a decision and you go, and then you just kind of check and make sure you didn't create a disconnected graph, right? So whatever remains has to be connected, just like we talked about in the first problem. So far we are good. I'm going to add C to my circuit, and then I'm going to make another choice. So I'm actually going to head back to A, and I'm going to delete this edge going from C to A. And I'll add A to my circuit because I'm looking at what's left, and it's still a connected graph here. Okay, so now I'm at A, and I'm going to take this bridge down to D, so I'll add D here. Now here's what you don't want to do. You don't want to go back to A. You don't want to use this bridge yet because you'll be trapped there. You won't have an edge that you can use if you go back to A. So we're not going to go that way. Instead, I'm going to go down here to B, use this bridge. Okay, and then I'm going to go, I don't have a choice. There's only one bridge there for me to take to get off of landmass B, so I'm going to take that back to C. Okay, so we're back at C, and then we really don't have a choice. We only have one bridge there, so we got to take that back to D, and then we would go back to A. And that completes my circuit. Okay. So Flurry is really a very simple algorithm to follow. Delete an edge, check and see if it's connected. If it is disconnected, undelete that edge and try another one. All right, so it does guarantee a way to find an Euler circuit, and it is very quick once you get used to it. All right, so let's take a look at this one. This one says Eulerize, right? So that means down here we're probably not going to have a path or a circuit. If we have to Eulerize something, that means that we need to change the graph by duplicating an edge to create a circuit or a path. All right, so we're going to Eulerize, and then we're going to find the circuit. All right, so let's go through. Let's see what we're dealing with here. So we've got degree of 3, 1, 2, 3, 4, degree of 4. 1, 2, 3. This has a degree of 3. 1, 2, 3. Degree of 3 and 1, 2, 3. So this one has a degree of 3. So there is certainly an issue with this graph. There is no Euler path or Euler circuit with the way it is currently. So we are going to have to Eulerize. And remember, when you Eulerize something, you can only duplicate an existing edge. So for instance, there is no edge that connects B and C right now. So I cannot just willy-nilly create an edge here. However, there is an edge that connects C and D. I can duplicate that edge like this, and then these degrees would change to 4. Okay, so now I have these all even. These are two odd. So right now there's a path available, but they specifically wanted a circuit. So I'm going to duplicate this edge going from B to A. So I'm going to duplicate it. There it is. And then these would change to a degree of 4, and now they are all even. Now by duplicating those two edges, there should be an Euler circuit available in here somewhere. All right, so I'm going to switch back to, I don't know, let's say this color. There we go. And let's start our circuit at, let's start it at A. Why not? First letter of the alphabet. There we go. So I'm at A, and I'm going to go down to E. So I'm going to delete this edge first, right? Just using flurries again to find that circuit. Go. And then I'm going to go to D, right? And if you've been watching my videos, you're going to notice like my strategy with flurries is just to try and stay on the outside as much as possible and not go to the inside until I absolutely have to. Okay, so we went to C. And then, so now I'm going to have to kind of venture inside of the graph here. So I'm going to go ahead and go to A. I don't think that's going to create anything that is disconnected here. So check my graph. I think we are good. Yes, we are. We are still connected. All right, so now I'm sitting here at A. Let's go around the outside again. So let's go up to B. You don't have to use my strategy, by the way. You don't have to stay on the outside if you don't want to. There's several different ways to find this circuit. All right. So then, now here's the thing. I don't want to go back to A, right? Because there's only one edge, and I have to end my circuit at A, right? So if I go down to A now, I trap myself in there and I have no way to get to the rest of the edges in this graph. Okay, so I'm not going to go to A yet. Instead, I'm going to go down to E. So I'm going to delete that and go down to E. And from E, I'll only have one choice. There's only one edge leading out of E, so I have to take E over to C. All right, and then I'll only have one choice there, so I have to take C down to D. And then I only have one choice, so I got to go back to B. Hopefully this works out. There we go, so to B. And then, yes, this will work out, so this will take me back to A. Yeah. There we go. And that completes my circuit. All right, so that worked out nicely. Okay. So don't be intimidated by flurries. It is actually a really quick and easy algorithm that'll guarantee you the Euler circuit, and there is a little inherent danger in just kind of guessing and checking your way through the circuit. It can take a lot of time and you might miss something which would produce a circuit that's not a circuit, so you don't want to do that either. Stick with flurries. It's the way to go. All right. Here we go. This one says find the circuit produced by the nearest neighbor algorithm. I made a slight typo here, so I'm going to fix that. I want you to find the Hamiltonian circuit, okay? Specifically a Hamiltonian circuit produced by the nearest neighbor algorithm, starting and ending at vertex A. All right, so the definition of a Hamiltonian circuit tells us that we must visit every vertex exactly once and return home. Okay, so we don't have to use every single edge, but we do need to visit every single vertex. All right, now nearest neighbor is a real simple algorithm to use. They specifically want the circuit produced by nearest neighbor, so you have to use nearest neighbor algorithm here. All right, so we're going to start our circuit at A because that's exactly where they tell us to start. And nearest neighbor is real simple. All you have to do is take the edge that is the shortest each time. Okay, so notice here this edge is 10. This edge has a weight of 13. This edge has a weight of 12. So we're going to take 10 first. Okay, so I'm just going to mark my path here. So we're going to go A to E, and then we're going to go, we got to look at E, so we have a 15 and a 3 coming out here, so we've got to take the 3. You always have to take the shortest edge. So we're going to go from A to E to C. Now once we're at C, our options are 14 and 8 here, so 8 is the shorter one, so I'm going to go down here, travel to D, and then once I'm at D, my options are 11 and 12, so 11 is the shorter one, so I've got to take 11 over to B. And you might want to take stock of, like, hey, we visited this vertex, we've visited this vertex, and this vertex. So there's only one vertex left, right? Because I have options. I have 15 and 9. 9 is the shorter one, but 15 also leads back to a vertex I've already visited. So I'm going to go back to F, add that to my circuit. F has now been visited. So everything's been visited, so I've got to return home back to A. And that completes my Hamiltonian circuit. All right. The other thing you want to do is make sure that you add up the total cost of your circuit. So with this one, you would just add up the edges that you use. So that should be 10 plus 3 plus 8 plus 11 plus 9 plus 13. So you should get a total weight of 54. All right, guys, that's it for our review today. Have a great day. Good luck on the practice problems.